Hi, my name is Mr. Peck from Ideas Inc. School, and I am here today to talk about electricity part 1. This chapter is a continuation from what we have learned from primary schools. In this chapter, we will be discussing about 3 new concepts. Number 1, resistance. Number 2, current. And number 3, voltage. First, let's talk about resistance. The resistance of a component is the ratio of the potential difference across to the current flowing through it. The standard international unit for resistance is ohms, and the symbol for resistance is the omega psi. There are 2 types of resistors. A fixed resistor is a component that reduces the current by a fixed proportion, while a variable resistor, also known as a rheostat, is a component that allows the resistance to be adjusted. Now we will discuss how to calculate the total effective resistance across 2 points on a circuit. Resistors can be connected in series or parallel. If the resistors are connected in series, their total effective resistance is simply the sum of all the resistors. If the resistors are connected in parallel instead, the resistance must first be converted to a reciprocal fraction before being summed up together. After that, the amount will be inversed to obtain the resistance. Finally, we will be looking into how the length and cross-sectional area of a wire can affect the resistance. With regards to length, the longer the length of wire, the greater the resistance. Thus, the length of wire is directly proportional to its resistance. Now, with regards to the cross-sectional area, note that the wider the area, the lower the resistance. Thus, the cross-sectional area of a wire is inversely proportional to its resistance instead. Now we will be discussing about current. There are 2 types of current flow. They are conventional current and electron flow. Conventional current always flows from the positive terminal of the battery to the negative terminal, while electron flow will always move in the opposite direction from the negative terminal to the positive terminal. The standard international unit for current is amperes. The definition of current is the rate of flow of charged particles. This is the amount of charges flowing past a point every second. For example, 1 ampere means that there is 1 charged particle flowing across a point every second. Thus, 3 amperes will mean that there is 3 charged particles flowing through a point per second. The device used to measure current is known as an ammeter. An ammeter is a device that has a very low resistance, therefore it can be connected in series without affecting the overall resistance of the circuit. Next, we will be talking about the concept of voltage. The standard international unit for voltage is volts. Voltage is the potential difference across 2 points on a circuit. The definition of voltage is the work done in driving a unit of charge through 2 points in a closed circuit. These 2 points can be across a bulb, a resistor, or across a battery. When measuring the voltage across a battery, we call this the electromotive force, or EMF for short. This is the work done by a source to drive a unit of charge around a complete circuit. But for all intents and purposes, potential difference and EMF are both referring to voltage. The device used to measure voltage is called a voltmeter. A voltmeter is a device that has a very high resistance. As a result, when measuring the potential difference across a component, the voltmeter must be connected in parallel to ensure that its high resistance does not affect the circuit. When connected properly, the high resistance of the voltmeter will deter current from flowing through it. On to the main part of the chapter. In this section, we will be discussing Ohm's law. Ohm's law states that the potential difference across a conductor is proportional to the current passing through the conductor. This is provided that the physical conditions and temperature are kept constant. In summary, Ohm's law is simply the formula of voltage being equal to current multiplied by resistance. This is summarized in the formula V equals I times R. Let's now discuss how Ohm's law is applied to a series-only circuit. It is extremely important to memorize the laws of a series circuit first. The 2 laws are: Number 1, the current flowing through the series circuit is equal throughout. Number 2, the sum of potential difference across the resistors will always add up to the EMF of the battery. Please look at the example given in the notes. Without the notes as reference, what I am about to describe will be confusing. Pause this audio recording and take some time to study the circuit shown. Let's begin. First, let's calculate the total effective resistance. Since the resistors are connected in series, the total resistance is the sum of the 2 ohm and 4 ohm resistor, making it 6 ohms overall. The next reading to find is the circuit current. The circuit current is the current that the battery produces. This is the conventional current that is coming from the positive terminal of the battery. To find it, we will apply Ohm's law. Since the current is equal to voltage divided by resistance, or I equals V divided by R. If we take the voltage of the battery, 12 volts, divided by the total resistance of the circuit, 6 ohms, we will be able to obtain the circuit current. This will amount to 2 amperes of current. Since the first law of series states that the current throughout the circuit is equal, both the ammeter 1 and ammeter 2 readings will be equal to 2 amperes each. Finally, let's calculate the potential difference across each resistor. To find the voltage across the 2 ohm resistor, we will need to apply Ohm's law again. Just take the current of 2 amperes and multiply it by the resistance of 2 ohms to get a voltage of 4. And to find the voltage across the 4 ohm resistor, we will just need to multiply the same current of 2 amperes with the resistance of 4 ohms to obtain a voltage of 8. Let's check if what we did is correct up till this point. Since the second law of series states that the sum of the potential difference across all the resistors must add up to the EMF of the battery, if we add up the voltages across the 2 and 4 ohm resistors, we will get 12 volts, and that is the EMF of the battery. And thus we are correct. Next up, we will be discussing about how Ohm's law is applied to a parallel-only circuit. Please memorize the 2 laws of parallel circuit first. The 2 laws are: Number 1, the current will split upon reaching the junction of a parallel circuit. Number 2, the potential difference across parallel wires are equal. Once you have memorized the laws, please look at the example given in the notes. Without the notes as reference, what I am about to describe will be confusing. Pause the audio if needed and study the circuit shown. Let's begin. First off, we will be calculating total effective resistance. Remember to reciprocate the resistance first before summing them up and inversing it. If you have done so correctly, the total resistance will amount to 2 ohms. Next, we will be looking at circuit current again. Please recall that circuit current is the current that is flowing out of the positive terminal of the battery. To find it, we will apply Ohm's law. The circuit current can be found by taking the EMF of the battery, 12 volts, divided by the total resistance of the circuit, 2 ohms. As a result, the circuit current will be 6 amperes. Now we will apply the second law of parallel circuits. Since the potential difference across the parallel wires are equal, both the readings of voltmeter 1 and voltmeter 2 will be 12 volts. Finally, to find the reading of ammeter 3 and 4, we will apply Ohm's law by taking the voltage across each wire, 12 volts, and dividing it by the resistance found on each parallel wire respectively. Thus, ammeter 3's reading will be 12 volts divided by 3 ohms, amounting to 4 amperes. And ammeter 4's reading will be the same 12 volts divided by 6 ohms, amounting to 2 amperes. After all that's said and done, let's check if we are correct. Due to the first law of parallel circuit, we are aware that the current will split upon reaching a junction. Thus, when we add up the current flowing through the parallel wires, which are 4 amperes and 2 amperes respectively, we should get the same as the circuit current of 6 amperes. On to the last part of the chapter, we will be discussing a circuit with both series and parallel components. This will be the most difficult part of the chapter, so if you are still unsure, please listen to the audio clip again or approach Mr. Peck for clarification. Please take a look at the example in the notes. Without referencing the notes, what I am about to discuss will be confusing. Once again, pause this audio clip and study the circuit carefully. Let's begin. When dealing with a circuit with both series and parallel portions, always calculate the series part of the circuit first, as that is the easiest thing to do. The total effective resistance can be found by adding up the resistance in both series and parallel. This will amount to a total of 8 ohms. Next, we will attempt to find circuit current. We can do so by taking the voltage of the battery, 12 volts, divided by the total resistance of 8 ohms. That will give us a circuit current of 1.5 amperes. Due to the first law of series circuits, all the resistors connected in series will experience the same current of 1.5 amperes flowing through them. As a result, both the ammeter 1 and ammeter 4 reading will be 1.5 amperes. To calculate the potential difference of the resistors in series, meaning voltmeter 1 and voltmeter 4, we will take the circuit current of 1.5 amperes and multiply it by the resistance of 2 ohms and 4 ohms respectively. Thus, the voltmeter 1 reading will be 3 volts while the voltmeter 4's reading will be 6 volts. Now on to the parallel section of the circuit. Because the battery is ultimately the source of all the work done in the circuit, we can calculate how much voltage is left for the parallel portion by simply subtracting the voltage of the battery, 12 volts, with the total voltage from the series part of the circuit, which was 9 volts. As a result, only 3 volts remain for the parallel portion of the circuit. By applying the second law of parallel circuits, both the voltmeter 2 and voltmeter 3 readings will give the same reading of 3 volts. Using this information, we can easily obtain ammeter 2 and ammeter 3 readings. Ammeter 2 can be found by taking the voltage of 3 divided by the resistance of 3. This will get us 1 ampere. While ammeter 3 can be found by taking the same voltage of 3 divided by the resistance of 6. And this will get us 0.5 amperes. Now let's check our work. If we add both the emitter 2 and 3 readings, which are 1 amperes and 0.5 amperes respectively, we will be able to get back the circuit current of 1.5 amperes. Thus we are correct. We have come to the end of electricity part 1. In the next audio clip, we will be discussing about the practical uses of electricity. If you have any doubts, please approach Mr. Peck. Thank you for listening and have a nice day.